I'm Professor Caudill, and we're still on units of measurement. So today, picking up where we left off. Um, Again, I think I underestimated this chapter. Um, I thought it'd be more intuitive than I thought. So here we have estimating surface area of the Earth. I think last time we might have left off around here. For answers, underestimate or overestimate. So we can give it a shot. I don't know if we'll get much traction, but so let's say mass of the Earth, of the atmosphere. Mass of the Earth's atmosphere is 10 to the 19. Now, let's see, now the density of the Earth's atmosphere is 1 kilogram per meter cubed. So as we know, we get mass from volume times density. I think that's how it. I think that was a recommended course. But we already have, so we have density, we have the mass already. Explain the height of Earth's atmosphere. So 10 to the 19 is our mass, equals 1. So we have 10 to the 19 kilograms. Is density is 1 kilogram per meter cubed. So we know this has to be, I think it has to be times a volume. Let me double check. Get a secondary source. Mass is calculated by density times volume. Mass is multiplying it. Okay. Density is mass over volume. Mass is density times volume. Okay. Mass is density times volume. So mass is density times volume. So we know the mass, we know the density. Volume, so it's asking us to get the height. So we know height is one dimension of meters squared, of cubic meters. So we need to get one dimension of height. So 10 to the 19 equals. So I think the density is simple. So what we really want is, yeah, I'm not really sure. So let's just move on. For practice estimating, all right, let's try this. Page not found. That's unfortunate. All right, moving on. Significant figures. So, relationship between constant accuracy, precision, uncertainty, discrepancy. So, if you recall, physics is as precise as the tools used and let's say tools used and measurement standards. So we have two instruments. Digital scale has replaced the double pan balance. Is more accurate, more precise. What do we mean? Science is based on observation and experiment. That is, in other words, measurements. Accuracy is how close a measurement is to the accepted reference value. So, hold on, let me get a timer going. Let's do. All right. Accuracy is how close a measurement is to the accepted reference value. For example, let's say we want to measure the length of standard printer paper. Package we want to purchase is 11 inches long. Then we measure the length of the paper 3 times to find the following measurements. Quite accurate because they're very close to reference value. Not be very accurate. Constant requires an accepted reference value. Precision is how close it is between measurements. So these are all kind of, I feel like it's kind of obvious, but I'm sure they'll make it less obvious. Measurements in a paper are both accurate and precise. GPS. GPS measurements are spread out far from each other. They're relatively close. So this thing gets a low precision and high accuracy. So we have some useful visual aids. High accuracy, low precision, low accuracy, high precision. So I guess the center is the true measurement. So high accuracy means you're getting an even spread within the true measurement. High precision means you're getting equidistant, I would say. Precision of measurement is related to uncertainty. Accuracy is related to discrepancy. The accepted reference value, so that'd be our measurement standard, like time, it's on a cesium atom or something like that. How much your measurement values deviate from one another. Biggest to smallest. Find the standard deviation of measurements. It's like a bell curve, maybe. If I remember right. Discrepancy. Difference between the measured value and the measurements are not very accurate, then the discrepancy is very high. So we might average 3 measurements to say our best guess is 11. Yeah, so these are our measurements: 11.1, 11.2, 11, 10.9. You could just do, so this is n, so this is n equals 3. We have 3 measurements, so if you wanted to find the average, it's n over, it's the sum of each n over n. Each element of n. So let's say this is big N, okay, which is 3. So we would take the sum of little n's, each little n over big N. That makes sense. So basically what this would be saying in this scenario is 11.2 plus 11.1. Now I swap those, 10.9 over 3. So that's just a formula for average. And might get 11.0. inches. Provides a quantitative measure of accuracy. We might calculate the uncertainty, our best guess, by using half the range of our measured value. 0.15 inches. Length is plus or minus 0.15. Half the range of our measured values. So what's the range? It's 10.9 to 11, that's 0.1 plus 0.1 plus 0.1. So the spread is 0.3. So the uncertainty is roughly 0.5. So uncertainty is the min, let's say it's the max of n minus the minimum of n equals 0.3, and that's divided by 2, and that's roughly, uncertainty is roughly the max of n minus the min n divided by 2, which is over 2 equals 0.15. Okay. Length of paper is this plus or minus 5. Okay. Uncertainty is a measurement, and a measurement A. It's often read delta. So like that. I'm not used to writing deltas. Delta. Okay, delta A. Our measurement A, delta A, is the uncertainty. So our measurement would then be plus minus a. Measured length of the paper, we express this. Since the discrepancy of this is less than the certainty, I'd say our measure about agrees. Alright, so limitations of the measuring value. This affects the uncertainty, the skill, the person taking the measurement, irregularities of the object being measured, and any other factors. And looks like they missed the measurement standard, I think. In our example, if such factors contributing could be smallest divisor on the rule 1/16th. Person using the rule has bad eyesight. Ruler is worn down on one end. One side of the paper is slightly longer. Percent uncertainty. Another method expressing uncertainties as percent of the measured value. The measurement A is expressed with uncertainty delta A. The percent uncertainty is defined as times 100%. All right. Let's do some work finally. Calculating percent uncertainty of a bag of apples. All right. Grocery store sells 5 pounds of apples. 5 pounds of apples. We buy 4 bags per bag, and we bought 4 pounds in a month, and weigh the bags each time. So roughly 20. We then determine the average 5 pounds is 5.1 plus minus 0.3. Okay, so they determine that, but can we determine that? So 4.8 plus 5.3 plus 4.9 plus 5.4 divided by 4 plus, that would be the max, it's 5.4 minus the min, 4.8 divided by 2. So that's going to be our measurement. So 4.8 plus 5.3. All right, 4.8 plus 5.3 plus 4.9 plus 5.4 divided by 4. So that's 5.1. All right. 5.4 4 minus 4.8 divided by 2. It's 0.3. All right, so we are agreeing with the textbook here. What is the percent uncertainty? Oh, okay, I missed it. So you take the, what is this called? Delta A. What was delta A called? Uncertainty divided by the measurement. Uncertainty divided by the average measurement. All right. So basically, they want 0.3 divided by 5.1, which is saying you want 3/10 divided by 5 and 1/10, or 51/10, which is saying you want 3/10 times 10, 51, which is 30, 510. These cancel out. 3/51s. So 3 divided by 51. We're going to get this. So that's 0.058. Let's round it up. Let's say 0.6 times 100% is 6. See if the book agrees. And the book does agree. So we conclude the average weight of the store, average weight of the bag of apples from the store, percent uncertainty. So we're getting 5.1 pounds plus 6, plus or minus 6%. So that's what we are expecting to get from the store. Notice the percent is dimensionless because the units of the weight can cancel. We took the ratio. Check your understanding. All right. Start a new project. High school track coaches just purchased a new stopwatch. Stopwatch manual states a stopwatch has an uncertainty of 0.5. So our delta of the runners, delta of the stopwatch is plus minus 0.05 seconds. Runners on the track coach team regularly clock 100-meter sprints. So our measurements are 11.49. Seconds. At the school's last track meet, the first place sprinter came in at 12. So we get this additional data, 12.4 seconds and 12.0 seconds. Will the coach's new stopwatch be helpful in timing the sprint? Why or why not? Okay, so let's get the average, 4.9. And so let's say this is our S average. So we take S average plus delta S over S average times 100%. $13.5, so 13.25 plus 5, 13. So okay. So our baseline is 13.25 plus or minus 4%. So what we want to know is if these values are within this value. So you can see 12 is lower than 13, so we want to take 13.25 minus 0.4%. So 13.25 minus 0.4%. Which is, let's see, 12.85. So I'm gonna say no, but I don't know if the if just doing this is right. It might be 0.4 times 13.25, which would be way lower. 4% is 0.04, my bad. 12.72. So I'm gonna say no. Okay, let's move on. Uncertainties in calculation. How big is the uncertainty is something you calculate by multiplication or division. So the uncertainty, if the measurement going into a calculation have small uncertainties, percent or less, the method of adding percents used. The method states the percent or uncertainty in a quantity calculated By multiplication division is the sum of the percent of the uncertainties. Okay. Method states the percent uncertainty. So delta A over A times. So it's saying the percent uncertainty in a quantity calculated by multiplication or division. So it's saying Q is also the sum of the percent uncertainties. So sum of the percent uncertainties and the items used to make calculations. So I think this is what it's saying. It's saying another way of saying this is you can just sum each individual uncertainty. So let's see if that is what he's saying. Example 4 has a length, so 4 so I'm looking at a floor. It's got a length of 4 and a width of 3 with uncertainties of 2 plus minus 1%. Then the area of the floor is 12 meters. Then the area is, because it's length times width, is 12 plus or minus 3%. Okay. Express as an area. This is all right. So let me make sure I'm getting this right. So 12 minus 3%. 12 is this. Or let's do this. 0.36. Okay, so I am getting this right. So it's 12 minus 3% of 12. So 12 plus 3%. 12 plus minus 3% is another way of thinking it is like 12 plus or minus 0.03 times 12. So it's 3% of 12. And obviously the book rounds up to 0.4. Precision of measuring tools and schemes of gears. Alright, so important factor in the precision of measurements involves the precision of a measuring tool. Precision of measuring tools, one that can measure values in very small increments. Standard ruler can measure length to the nearest millimeter. Caliper can measure the nearest 0.1 millimeter. It can measure extremely small distances and length. More precise measuring tool, more precise measurements. Pretty self-explanatory. When we express measured values, we can only list as many digits as we measure initially with our measuring tool. Okay, so you can't. So if you have an accuracy of 0.01, you can't get 0.0001 with accuracy. So he's basically restating this. Cannot get this because our measurements were not precise enough to measure those smaller values. The person measuring the length of the stick with the ruler notices the length of the stick seems to be between this and this, and he or she estimates the value of the last digit. Using the method of here, the ruler is that the rule is that the last digit written down in the measurement is the first digit. Rule is that the last digit written down in a measurement. Okay. The last digit written down in the measurement is the first digit with some uncertainty. Okay. Value in a digit in a value. We need significant digits in a value. We start with the first measured value at the left and count the number of digits through the last. The measured value is 36.7 centimeters, has 3 digits, has 3 significant figures, indicate the precision of the measuring tool. Special consideration giving to zeros when counting. Zeros are not significant because they are placeholders that locate a decimal point. These are the two significant figures, zeros, and these. So, but these ones are significant. This number has at least 5 significant zeros, 5 significant figures. That could mean a number is known last digit. So 1300 could have 2, 3, or 4 figures. We should write 1300 in scientific identification like this. 1.3. Where there's 2, 3 zeros are significant except when they serve only as placeholders. Okay. So that was a mouthful. Significant figures and calculations. Combining measurements with different degrees of precision, the number of significant digits in the final answer can be no greater than the least precise measurement value. Multiplication, the result should have the same number of significant figures as the quantity with the least number of significant figures. The area of a circle can be calculated by r squared. Let us see how many significant radius has only, say, r 1.2 meters. We could calculate 3.4 times this equals 4.2. Because the radius is only 2 significant figures, 1.2, it limits the calculation to 4.5. For addition and subtraction, the answer contained no more than the least precise. By 7.56, then drop off 6 point this. Go home, add 13.7. So you're getting okay. So not really sure. I think they could have written this part better. Significant figures in this text. In this text, most numbers are assumed to have at least 3 significant figures. Consistent numbers of significant figures are used in all word examples. Answer given to 3 digits is based on input to at least 3 digits. Care is also taken that the number of significant figures is reasonable for the situation. The more accurate numbers are needed, the more we use 3 significant figures. Finally, if a number is exact, such as 2 in the form, it does not affect the number of significant figures. Likewise, conversion factors such as 100 centimeters divided by 1 are considered exact and do not affect the number of significant figures in the calculation. Alright, so there's a lot of caveats to significant figures. Solving problems of physics. Alright. Maybe this will be more fun. Describe the process for developing a problem-solving strategy. So, like, what is the purpose? Why, at the AI2C, are we studying physics? What problems are we trying to solve? We are trying to automate all human labor in the current intelligence community. So what labor do? They mostly do remote sensing. They do communication intercepts. Just generally knowing about like military intelligence, knowing what the adversary is doing, what they're thinking. So a lot of it is prediction. The problem is predicting threats, predicting what another person's going to do. So if the problem is predicting what you need to do, let me write this down. If you need to predict what adversary A, what adversary A will do, what do you need to know? You need to know the history of A. You need to know the psychology of A. You need to know the capabilities of A. So if the problem is to know these, to know the history, psychology, capabilities, you need remote sensing apparatus. You need, and yeah, it's all remote sensing at every level, even for human intelligence. Explain how to find the numerical solution to a problem. So, numerical solution to a problem. So if I have a satellite, say this is Earth, and I have a satellite, and I'm doing something in this medium to collect information. How to find, so I need to know how many, let's say, numerical solution might be how many photons collected per second with measurement tools. So how many photons? So how precise can a surveillance satellite be? So it is funny that how outdated these calculators are. Like, disgusting. Okay, so problem solving skills are clearly essential to success in a quantitative course in physics. The ability to apply broad principles, usually represented by equations, to specify situations is a very powerful form of knowledge. It is much more powerful than memorizing a list of facts. Analytical skills and problem solving can be applied to new situations where a list of facts cannot be made long enough to contain every possible circumstance. Such analytical skills are useful for both problem solving in this text and for applying physics in everyday life. Alright, so a certain amount of creative insight is required to solve problems. No rigid procedure works every time. With practice, the basics of problem solving skills become almost automatic. That's pretty cool. I didn't know that. But the goal for the AI2C is for an intelligence community to do its own problem. Like, there shouldn't be anyone working in an intelligence community besides automated machines. Like, national security should be completely done without humans in the loop. Just like self-driving cars, they're safer. It's safer to be driven by a Tesla than a Ford 2015 Ford or something. So why not national security? One way to get practice is to get workout test examples for yourself as you read. Is work out the text examples. And another is to work out many ends of section problems as possible, starting with the easiest and then progressing to the more difficult. To become involved in physics, you will see it all around you. You can begin to apply different situations you encounter. Alright, so this is like why we are here. Although there is no simple step-by-step method for every problem, following three-stage process facilitates problem solving and makes it more meaningful. Strategy, solution, and significance. Strategy. So what's our strategy? Strategy is to automate everything. The solution is to automate everything. And the significance is a more enjoyable life for humans. Why work when you don't have to? Who wants to spend their possibly one lifetime working a day-to-day job, So yeah, strategy is to automate away human labor. So the strategy is to find what we can. It's like, how do you separate strategy from solution? They're so intertwined, I guess the strategy is kind of how you get to the solution. So if the solution is automate every human labor, the strategy might be start at what do you know how to automate? Like for me, I know how to generate random equations that helps you learn math faster. So that's one strategy. if you're trying to learn better. But if you're trying to automate learning, where do you even start? Well, you can start by collecting data. So collecting data, feedback. All right, let's move on. I guess we're going to talk about these in-depth strategies, beginning stage of problem solving. The idea is to figure out exactly what the problem is, develop a strategy for solving it. Some general advice for the strategy is examine the situation, which physical principles are involved. So which of the 7 quantities might be involved? So photons maybe have luminosity, definitely speed of light, and yes, speed, seconds, distance, maybe length. I don't think photons have mass, so it wouldn't involve mass. I mean, the satellite would have a mass itself. All right, so it often helps to draw a simple sketch at the outset. So as I did, simple sketch. You often just need to decide which direction is positive and no on your sketch. So, like I said, photons per second. So now, if the goal is to maximize photons collected per second, that gives us, we can start getting our mindset into what equations are best for photons collected per second. Well, finding the correct equation is essential. Keep in mind that equations represent physical principles, laws of nature, and relationships. Without concept understanding of a problem, numerical solution is meaningless. Make a list of what is given or can be inferred, as stated. Many problems are stated very succinctly. Alright, so identify what needs to be determined, identify the unknowns. So the unknown in this course is what can't be automated, what can. Determine which physical principles help you solve the problem. It's easiest to find equations that contain only one unknown. That is, all the variables are known. Equation contains more than one unknown. The additional equations are needed to solve the problem. Some problems, several unknowns must be determined to get at the one most needed. So keep the physical principles in mind before getting astray in a sea of equations. You may have used 2 or more different equations to get the final answer. So the solution is when you do the math. Okay. So solution would be have an abstract representation. Solution might have an abstract representation of a satellite. So it's like maybe also in a simulation, like an abstract or a simulation of what you're imagining. So basically, solution, in other words, do algebras, calculate geometry, or arithmetic necessary. I wish it would have added like compute, like you need to, or I think it wants you to abstract the solution and then maybe that's in the significance part, but so algebra, calculus, geometry, or arithmetic necessary. After done in the math, it's tempting to think you're done, but physics is not math. We use mathematics as a tool to help us understand nature. You should always assess the significance. Check your units. Check the answer to see if it's reasonable. Does it make sense? We want to describe nature accurately, so we don't want to get lost in the sea of what can we automate, what can't we in the dreamscape. We want to know what in nature can be automated. Not that we're trying to automate nature, but we're, humans live in nature, and humans need resources, need to defend resources. So, how do we automate our needs? How do we have to be constrained to living always worrying about resources, or can we delegate our concerns to automation? Can a robot babysit us? And to know if a robot can babysit us, we need to know how to describe our needs and how to get our needs from nature. And its sign, in addition to its unit sign, usually tells you about its direction. Check to see whether the answer tells you something interesting. What does it mean? This is the flip side of the question. Does it make sense? Does it tell you something interesting? Understanding nature. So physics is to understand what the limits are of automating. So we can be babysit by robots. We solve physics problems to learn a little something about how our nature operates. Assuming the answer does make sense, you should always take a moment to see if it tells you something about the world that you find interesting. Even if the answer to a particular problem is not very interesting, what about the method you use to solve it? So this is very important. Oftentimes, you learn a method, it can be applied, it can be generalized, and that's the most important part of learning is when you go from the romance. I saw this in a lecture. Go from romance to precision to generalization, and it's always a repeated process. You want each step to be kind of equal. Romance, precision, generalize. So this is basically saying to generalize. The method be adapted to answer questions you find interesting. In many ways, it is in answering questions such as these that science progresses. So science progresses in generalizations. So chapter review, key terms, accuracy, basic quantity, conversion factor, base unit, dimensions, discrepancy, theory, uncertainty, physics, order of magnitude, metric system, kilogram law, meter. The equations are percentage uncertainty, delta A over A times 100%. So summary, scope and scale of physics. It's about trying to understand simple laws, operate on a vast range of scales. So base units, kilograms. So in this course, part 1, we're limited to meter, kilogram, seconds. Be careful when you're converting units. dimensions. You have to make sure you get them match dimensions. Estimates are as important as precision for building intuition. Significant figures are relevant. Solving problems, physics, strategy, solution, significance. So, conceptual questions: what is physics? In terms of the validity of a theory. So next lesson we'll pick up with problems, and then we can move on to the next chapter. So thank you guys.